All right, welcome to video two. In video two, it's all about particle density. And particle density has some similarities to bulk density. Some people might say it's exactly the same but different, right? People love to say that about stuff, but it's not really like that. It's not the same, but it has some similarities to bulk density. So let's do the definition. So particle density is the oven dry mass of a soil divided by just the volume of solids. Okay. So whereas bulk density was the oven dry mass of soil, same numerator, divided by the total soil volume, here we're just interested in the space that the solid particles take up, not the entire soil volume. So you're going to use the exact same problem that we studied last time. Here we have our same soil. It weighs 106 grams, oven dry. Its solid volume is 40 cubic centimeters. Its pore volume is 40 cubic centimeters. Total soil volume is 80. And if we're going to calculate the particle density, which we are, and then we use the abbreviation as dP, that is oven dry soil over the volume of solids, just the solids, the space that the solids take up. So in this case, we got dP is 106 grams divided by 40 cubic centimeters. If you do the math, you get about 2.65 grams per cubic centimeter. Okay, 2.65 grams per cubic centimeter. And that is not surprising. And that's not surprising because the particle density of most of the soils that we encounter in temperate region soils, and we live in a temperate region here in San Luis Obispo, and most of the world, well, most of the world where people, well, no, I can't even say that, but almost all the United States is in the temperate region. And the particle density, let me go over here now. The particle density, whereas bulk density changes as a function of texture, structure, percent organic matter, content, and degree of compaction. Particle density, right? It's just another mass over volume, dP. It does not depend on any of those things. It doesn't depend on texture. It doesn't depend on structure. It doesn't depend upon organic matter, content, or the degree of compaction. What it does depend upon is the soil mineralogy, that is the types of soils that we find in a soil. And since in the temperate region, the dominant mineral, actually in most soils, the dominant mineral of most soils, and certainly in the temperate region, is quartz, right? What are the two most abundant elements in the Earth's crust? Silicon and oxygen, in the opposite order, oxygen first, then silicon, and those are the ingredients of quartz. So that's quartz. Quartz, as you know, looks like this. And guess what the particle density is of quartz? dP of quartz is, what do you think? 2.65 grams per cubic centimeter, right? Makes sense. So in general, right, we're going to make the assumption, we're going to assume that the particle density of most soils is 2.65. Okay, we're just going to keep that kind of in our back pocket, because since the ratio is oven dry soil mass over volume of solids, doesn't matter what texture is, it doesn't matter what structure is, it doesn't matter how much organic matter is in the soil or how compact the soil is. We don't care about anything that's going on in the pores. All we care is the mineral fraction and the solids in the mineral fraction. And if that's the case, then we make the assumption that the particle density is 2.65. So let's go here. So this is what we were looking at before, right? We got sandy loam granular, clay loam granular. We have bulk densities that are going to vary. All right. What's the particle density of this soil right here? Do we need to calculate it? No, 2.65 grams per cubic centimeter. How about our sandy loam granular? Has a bulk density of 1.5. Particle density equals 2.65. Nailed it. Okay, you get the idea. Clay loam granular over here, particle density equals 2.65 grams per cubic centimeter. Even if we go to any of the soils up here that we talked about, the loam granular that has 15% organic matter, particle density 2.65. Clay loam prismatic, the picture got a little messed up, but the particle density is 2.65 grams per cubic centimeter. The loam soil that's platy structure, or the loam soil that's been compacted a little bit, particle density is 2.65 grams per cubic centimeter. All right, you got that now. And once you have it, no one can take it from you. Okay, so this slide, I'm just showing you that the particle density is going to depend upon the minerals that are found in the soil, right? And we already said that most soils are quartz rich, so the particle density is 2.65. So that's a soil that looks like this, particle density of 2.65. But soils that are dominated by iron, especially iron oxides, right? Iron oxides. Like, where do we find iron oxide rich soils? Arid environments, temperate environments, or tropical environments. That's right, tropical environments. So in the tropics, their particle density is going to be different because the dominant mineral is iron oxide. And if you remember from your chemistry discussions before, the atomic mass here of silicon, which is the main ingredient, or one of the main ingredients, is, of course, 28.1 grams per mole. That of iron is 55.8, which is about double that of silicon. So since both of them have oxygen in them, silicon is like half as heavy as iron. We would expect then, if the particle density of a temperate region soil, which is dominated by quartz, is 2.65 grams per cubic centimeter, what is that of a tropical soil, which is dominated by iron oxides? What do you think? 2 times that, or about 5.25 grams per cubic centimeter. That is a soil that's dominated by iron oxides, and it's going to have a particle density that is similar, right, to that of iron oxides. Okay, that's it. So I don't think there's anything else that we need to talk about related to particle density. I mean, it's pretty simple, easy, painless, and straightforward, right? Soil physical property of soils. So in the next video, what we're going to talk about is we're going to talk about, if I can get this thing to, no, it's not what I want to do. Oh, shoot. What I want to do is pause this video, right? How can I do that? Let's close that. All right. Here we go. All right. Sorry that this is my outro. It's kind of sucky. But anyway, next video, we're going to talk about porosity. We're going to pull everything together. Okay.